Hello, welcome you all in the fluid mechanics lecture series. Today topic is derivation of continuity equations. Before going to the derivation of continuity equation, first I am going to tell about the Taylor series expansion. What is the Taylor series expansion? If we have a function f of space and time at a point x, y, z, and t, so at a near to this function, the points x plus dx, y plus dy, g plus dg, and t plus dt. So when we expand this function, so we will get this one. So this is called Taylor series expansion. So in a Taylor series expansion, here, so we will get this expression. So when the change in function only in x direction, so x plus dx, so we can write it, but there is no change in y, g, and like here I have not written t or in t direction also. So we can only write this one, f partial derivative of function f with respect to x into dx plus 1 upon factorial to double derivative of function with respect to x into delta x plus this one. So here, and similarly, if in place of f we have the u is the velocity in the x direction, right? So in this we can write this form, not similar to this one. But here we would because dx is very small, delta x is very small, so delta x is very small. So the higher order term we are neglecting higher order term. For example, delta x value is 0.1. So delta x square equals to 0.01 and delta x cube equals to 0.001. So this is the reason we are neglecting higher order term. So directly we can write u x plus dx and y, g and t. Directly we can write only this one, right? Because no change of other uh, means y and z and time also, right? So similarly, if a rho is there in density, the rho is density. So at a near point where x plus dx means increment in x direction only, so you can write this one. And if multiply of rho this one, so we can directly write in place of this one rho, we can write this one, and in place of u, we can write this one, right? So when we expand this one, so we will get this expression. So here we will neglect this term because delta x is very small, so square term is there. So this one become 0. So in place of this one, we can directly write this term, right? So here means if u rho into u in small distance dx, so we can write u plus dx this one from this above this one. So this equation we will use in a continuity equation derivation. So this is the reason I am explaining these things, right? So if here we have a cuboid, so in a flow field, right? In a flow field, this is the very small cuboid in a flow field. So in the mass flow rate in x direction, here density into velocity and into multiply by delta y delta y and delta z cross sectional area. So mass coming in this section, this cross section. So this cross sectional area is delta y and delta z, which is the perpendicular to the x direction, right? So rho into u, this become the mass flow rate. So this become mass flow rate in a x direction, right? So mx, I can write, right? So similarly, in dx, small distance in dx, so we can write this. This is we have already written in previous, right? In Taylor series expansion, we have seen this one, right? So net mass flow rate. So net mass flow rate in x direction, you can write means mass coming in and mass going out. So for example here, mass going out, mass coming in this one, and mass going out this one. So difference of this is the net mass flow rate, right, in x direction. So similarly in a y direction also, and y direction similarly we can write similarly mass flow rate in a y direction, right, this term, and mass flow rate in a z direction this. So net mass flow rate in x, y, and z direction this one, which is equals to the net mass rate of change of mass within the control volume. This is the rate of rate of change of mass within control volume, right? So, so if we will if we rearrange this one, so we will get this x. This is the continuity equation in differential form, right? So here for steady flow means at a point there is no change its property, right? So here property is the density, so there is no change. So this becomes delta rho by delta t becomes 0, means there is no change, right? So we can write this is right. For incompressible, we know for incompressible density is constant. Density is constant means there is no change with time, right? So this is constant. Here rho is constant, so it will come outside. So you can write it outside. So multiplication of two terms. That term one is rho and other term is this one. So this is equals to 0. So this is possible. Rho cannot be 0 because this is the density and its value is constant. Only possible is this term is 0, right? So this is known the continuity equation for the incompressible flow, right? Similarly, in case of 2D, so in a 2D, so there is third dimension is 0, is right. So we can write the continuity equation. This is for 2D, means here omega w is 0. This is not omega, this is w. Means velocity in z direction, that is 0. We can write this one, right? Okay, thank you very much.